Okay, I will switch to English. So, hello Neville, hello Igor, and
Oh,
could you please introduce yourself? And let's start with Neville.
hi, my name is Neville from Spotify. I'm a data engineer and I've been maintaining this library called Scio for data processing Scala, Apache Beam, and Dataflow. And I'm very happy to be here and talk about it.
And you, Igor?
Hi. Yeah, my name is Igor. I work at Klarna. It's a financial services company. I am in Stockholm at the moment, and I work as a data infrastructure engineer in a data reliability team. Yep.
Okay, I have two short questions for Neville. So, what do you think who will find this talk is most useful? Who is the audience of your talk?
So this talk is mainly for data engineers and to some extent machine learning or data scientists who are interested in complex and big scalability challenges and also correctness and type safety.
So, okay, I think that we can start the talk, and let's switch to Neville. Okay, you're on air.
Cool. So let's get started. So the talk today is about data processing with Scio. As I mentioned, it's a Scala library that we built for data processing on Apache Beam and Google Cloud Dataflow. So let's get started. So just a little bit introduction. About me. I've been at Spotify in the New York office since 2011, and that's around the time when we launched in the US market. I worked on several teams. Most notably, I worked on the music recommendation team that built some of the features that's very popular today, including like Discover Weekly, Release Radar, and then the last couple of years, I mainly worked in the data infrastructure side. So we build and maintain libraries, toolings for data processing, including both batch and streaming. And we also work with the machine learning and data scientists, engineers on these problems. And then previously, I worked at Yahoo Search around the time of early days of Hadoop, so like 0.20, and that was a really long time ago. So let's get started. You used our service before. We are audio streaming service for both music and podcasts, and we're available in a lot of markets with a lot of both paid and free users. We stream 60 million songs to hundreds millions of people every day, and then we also collect a lot of data from users, like what type of music or podcast they listen to, and user create contents like podcasts and playlists as well. So we collect a lot of data and then make use of them to make recommendations and other features. So Pivot, yeah. So this is we launched earlier this year in Russia and several other markets, and I hope you all enjoy the service so far. So very happy to be in this new market with a much big audience to our service. So just a little bit about some of the interesting use cases for our like data processing. Discover Weekly is probably one of the basic recommendation. So basically, we listening history in the last couple of months, building preference vectors, latent vectors to represent both users and the tracks music taste. And then we use an algorithm called approximate nearest neighbor lookup to find music similar to what you have listened to before, but you haven't discovered yet. And that's how we build recommendation systems. And this Discover Weekly was presented in a weekly new playlist that contains music you might like but haven't listened to before. And then we have several other similar features like that. Release radar is for new music that's just released on Spotify, and then many other similar ones. And then we use data not only for building recommendation features, but also for other use cases as well, like fan insights, data for content creators like labels and musicians, so they can tell what tracks fans like most and where are their the geographical or demographic composition of their fans, where are they from, what music do they like. So those are useful insights to creators as well. So
I have a question about that. Can you elaborate on like any particular feature, how it's implemented? Is it calculated daily, or do you just for a long time things you calculate just additional incremental stuff every day and then run all the query, or is it just one big calculation at the end of the year, for example?
So it depends. For example, Discover Weekly is computed, it's presented weekly, but computation happens daily because we have to, even every day we have terabytes or sometimes hundreds of terabytes of data coming in. So we do daily aggregations, and then over a week, we roll it into like a bigger computation. And some other features has to be refreshed daily, like daily mix, for example. So it takes just 1 day of information, the listening history, and update your recommendation. Wrapped, on the other hand, is computed yearly, but in some cases, the early iteration, it took an entire year's data worth of data, and that's hundreds of terabytes. And then we've over time optimized it to do like smaller incremental aggregations, and then a bigger one at the end of the year. So it depends. And I'll talk a bit more in depth later in this talk. Cool. Yeah, let's move on. So we mainly at Spotify use Scala for data engineering, and we also pretty big in open source and contribute back to the community whenever we can. So just a list of some of the open source projects, which I'll talk a bit more in detail later in this talk. And also we are on the advisory board of Scala Center, so we help giving feedbacks, help with Scala 3 migration, for example, at the moment, and contribute back whenever we can. So, and there are some like pretty big challenges for us at Spotify. So first is the volume of data. People listen to music all day, and especially like this in the current situation, like you're working from home, just keep the music running. And so we have a lot of data collecting from users, and we have a lot of data sets. Pretty much every feature you see in the Spotify app is powered by data in some form of or shape. And then, of course, Spotify is a pretty big and distributed company. We have offices in several countries, many cities. So lots of data engineers and data scientists working on these problems every day. So these are some of the challenges. And from an engineering infrastructure side, obviously having so many people working on so many problems, like poses more technical challenges like orchestration, discovery, and lineage of all these pipelines and data. And of course, we're now a public company. We care about user privacy and access control and make sure the data is protected. And of course, from myself, infrastructure engineer point of view, the observability, quality, the storage and productivity, efficiency of the data, and after all, like the cost of running these big data processing jobs. It's also a big concern for us, so we care a lot about these problems. So let's take a brief overview of the history of data at Spotify. So the next slide is probably one of the most circulated picture of early days at Spotify. I think that was our first ever Hadoop cluster almost 10 years ago in the Stockholm office. And there was an engineering problem, like the cluster was overheating in the warm summer Stockholm sunlight. So the engineers figured out a way to prevent it from overheating. Cluster. We moved through several different iterations. So from the very early on-prem, which no longer exists, to Amazon EWR for a while, and then because of the cost and latency requirement, we moved back to on-prem. Had one of the largest Hadoop cluster in Europe for a while, with 2,500 nodes, 100 petabytes of data, and 100 terabytes of RAM, and it processed a lot of data every day. And it was actually decommissioned and shut down around 5 years ago. I think one of the bigger problem was at the time we were growing so fast and collecting and processing so much data that the cluster couldn't keep up. And we actually ran out of rack space in the data center to actually expand the cluster. So at that time, there was a decision to move to the cloud because companies like Google, Amazon has so much more resources, and we can leverage that instead of putting our own data center. And a bit overview of the processing stack we've used over the years. Spotify started as a Python shop actually around 10 years ago, and we created a framework ourselves for MapReduce in Python called Luigi. So it acts both as a framework for executing MapReduce jobs and also for orchestration and scheduling, like chaining jobs into a complex DAG graph for execution. Python is nice for engineering productivity, but has some problems. It's not hyped, and the performance wasn't so great. So we run into challenges running like complex machine learning recommendation algorithms. And around 2013, we switched to Scala and Scalding, a library from Twitter that uh, that provides like a very nice type safe and then performant DSL that runs on top of cascading, a library that in turn converts or translates your job into Hadoop MapReduce jobs. And it was a huge performance boost for us and also productivity. And it just the functional programming side of Scalding just opened up like a whole realm of being able to write job and be confident in the correctness and performance of the job. And that was almost 7 years ago. And around that time, there were a lot of other frameworks popping up in the big data processing ecosystem, like Spark was popular for iterative, interactive machine learning jobs. So we explored it a little bit. We also adopted Storm and started doing like real time for some features that require like lower latency, for example, like ads targeting and then new user onboarding. So we need to be able to compute quickly and then provide new data or feedback. And of course, we have analysts, data scientists who want to do like just prototyping, quick prototyping in Scio. Hive was the go-to choice at the time for ad hoc analysis. So this is a big picture of the step that we've been through over the years. And then, as I said, we ran out of capacity in the data center, and also just the growth of our user base and the data amount of data we have to process. So we decided to check out some of the cloud providers at the time. So Google was one of the options we considered. And one of the first Google product we used was actually BigQuery. So Google is pretty well known as like a pioneer in the big data processing ecosystem. BigQuery was SQL-like execution engine similar to Hive, but has some really nice, interesting properties. It's originally from a Google paper 2010, the Dremel paper that introduced like columnar storage and a more optimized execution engine. So those two like significantly sped up our like data processing. For example, columnar storage has reduced the I/O compared to the full row scan we were doing in Hive at the time. And then Hive translates to MapReduce job, so which requires a lot of like shuffling and also spilling to disk. And then Google has BigQuery has its own execution engine, which optimizes a lot of the overhead in these cases. So it turned, as a result, it turned a lot of our lengthy queries that usually take hours to run into maybe in terms of tens of minutes or even quicker. So that was a huge productivity boost for our data engineers and scientists. And of course, it integrates really well with the rest of the Google ecosystem, which I'll talk about a bit more later. So that was one of the first cloud native product we looked into. And then we started migrating more on-prem self-hosted ones into the more like fully managed and just reduce the engineering. For example, we moved PubSub and then convert to Bigtable. And these cases are actually pretty easy because a lot of open source projects were modeled after like well-known Google papers or technology. So it was a fairly easy migration. And of course, we migrated much of the Hadoop stack, Scalding and Storm, into Scio on top of being on top of Dataflow today. So that's the main topic of this talk. And of course, moving from provisioning our own hardware bare metal servers to GKE was also a productivity boost because we can easily provision, scale up and down the cluster based on workloads and experimenting with features. So that was a plus. All right, so this is what today's picture look like. So we mainly use Scio, the Scala API, for everything data processing. It runs on Apache, on top of Apache Beam, mainly the Java SDK that Google built and open source, which runs on Cloud Dataflow, Google Cloud service that handles the provisioning of clusters, the heavy lifting of moving bits and bytes around virtual machines. So the run or the execution framework. And we use Scio, Apache Beam, and Cloud Dataflow with a lot of pretty much most of the main Google products as well, the big data processing products like BigQuery, Bigtable, TensorFlow for machine learning, and then Spanner is another relational database on Google Cloud. So let's also take a look at the history of, I think it's pretty important to recap the evolution of big data. So I think Google published the MapReduce paper in 2004, so that was 16 years ago, and then they published a bunch of other big data distributed system papers, which inspired a lot of the open source technology that we use today. So MapReduce, the open source counterpart obviously is Hadoop. They published the Bigtable paper, the NoSQL key value store, which inspired HBase and Cassandra. And then Flume and Millwheel were the two internal data processing frameworks for batch and streaming. And they later combined these two into this new idea of a unified batch and streaming processing framework called Google Cloud Dataflow. And then they open sourced the SDK to the Apache community as Apache Beam. So that's what we use today. And of course, I also mentioned Dremel, the BigQuery, the technology behind BigQuery, which inspired several Apache projects as well, like Hive and Drill. So let's talk about Apache Beam a little bit more. So it introduced this new idea of batch and streaming as a single unified ecosystem. So the argument was that actually batch is a special case of streaming where all your data are available at the processing time, which we'll look a bit deeper later. And it also has this idea of decoupled SDK and runners. So the SDK is what data engineer use to build their pipeline in the abstract tag a graph of execution, and you can build it in one of these languages, Java, Python, or Go. And people, I think, are building more SDKs even today. And then it translates the graph into code like Java, JARs, or maybe Docker containers to be executed on one of these runners. So today it supports Google Cloud Dataflow, Flink, and Spark. So this idea is like you can write your pipeline once and execute it on different frameworks, and also supporting both batch and streaming. So, and the unified batch and streaming model tries to answer these four fundamental questions about data processing. What results are calculated? So this is the most fundamental one in classic batch. Word count could be just summing up integers, and could be all the way to complex machine learning, like predicting whether a user will like a track or not. So that's what, and then where in event time are results calculated. Event time is when the event happens. So when user clicks a track button, or maybe when the log is produced by a server. And in batch, again, these event time are not super important because we already always collect data until all of them are available before we start the processing. But in real-time system, that matters, and because there's a latency from event time to processing time, like from the log event being produced to it's collected and delivered to the by Kafka pops up into our streaming system. So that's the next question: when in results, and sometimes there's production outage issues with network or servers crashing, and the events can be delayed, and that leads to the next question: how do we refine results, right? We want to do real-time counting of top tracks as soon as possible, but what if a server has to be restarted and it delivers some small batch of results later? What do we do with those? Well, the last questions try to answer that. And it's easier to visualize this in these four animations, actually. So the first one is, they also try to solve the same problem. The first one is classic batch. We only start the job when everything is already ready, written in big, HDFS or GCS files. And we start the processing by counting every element all at the same time. The second one, if we bucket our data based on when they happen in event time, then we can do sort of window batch, have a more fine-grained granular computation of hourly or maybe minute, count of this integer count. And the third one is streaming. And then we can see that there's actually an element, number 9, being late in the first window. So the streaming case, we have this heuristics, this green like curling line that basically try to predict when should we start processing window. And in this case, the number 9 was ignored because it arrived too late. So that leads to the last problem, like, can we correct our computation and then handle the late arriving number 9 by using accumulation? And in this case, it's possible because the computation is plus, and you can do it in an associative and commutative way. And certain computations, like unique number of keys, is harder because we have to retain the full set of data to be able to process that. So these are the 4 fundamental questions of batch and streaming. So why did we pick Beam and Dataflow as our processing stack? I mean, there were some attractive properties. But first of all, it's fully managed and hosted, which means we don't have to maintain a Hadoop cluster anymore. We were at the time, the last final days of Hadoop cluster, running into a lot of scalability issues, like name nodes being down all the time because too many files and too much data. And this scales really well because on Dataflow, Beam and Dataflow, each job spins up its own cluster using virtual machines, and they have auto scaling that scales up and down based on the workload. Google also has a shuffle service which handles I/O in a much more efficient way than writing to tiny VM disks. And then the last point, it integrates really well with the rest of the Google ecosystem. So it has connectors for read and write. Any of these many other storage systems available to us. And we use Beam with Scala because Scala offers some very interesting, nice properties on top of the Java, which is the predominant language for big data processing. So in Scala, we can write very concise DSL. That's just more productive for data engineers. And there are already a lot of similar frameworks out there, Scalding, Spark, and Flink, that offer very similar APIs. So it's easy to onboard new developers. Functional programming is a natural fit for data. So the idea of like taking an immutable collection and applying like flat map functions and then compose them to construct our computation. And then the next point, there are already a lot of numerical libraries out there for machine learning. Like, for example, Breeze is similar to NumPy in Python. So like linear algebra, and then Algebird's Twitter library for approximate and parallel distributed computation, like things like Bloom filters or hyperlog. So it's very nice to have these things available for our processing. And the last point is Scala is one of the more powerful tool like macros for code generation. And for us library builders, it's super useful to be able to build libraries that's easy to use and handles a lot of the boilerplate, error-prone, like handcrafting problems that users facing every day for like dealing with data, like schema management and data type conversions. So this is when we introduced Scio. We built it as a Scala library for data processing. And the name is actually Latin for I know I can, and it just fits because it's a Scala library. Name starts with Scio and process data, so it ends with IO. So I find it a pretty nice fit for this library. And so built on top of Apache Beam's Java SDK. And it allows us to do unified batch and streaming processing and on one of these runners. Dataflow is the main runner that we use. And also, it's also open source, so check it out. A very minimum work on examples, very similar to if you're familiar with Spark or Flink. So again, we start with the context that abstracts the job execution graph. You can read text files, splitting each line by white spaces, filter the empty strings out, and then come by value, store it to a text file. And then we run the graph that triggers the execution. And then a slightly more complex algorithm, but still like fairly concise, this time PageRank. So the input is a tuple to two strings, the from URI and the to URL. And then we grouped from the from, assign each outgoing direction a rank of 1, and then we do iterative, 10 iterations by redistributing the incoming rank across all its outgoing links. And then we sum by dampening, like by applying a dampening factor of 0.85. So that's just a very basic and primitive PageRank expressing 13 lines of Scala. All right, one of the most interesting or unique features in the early days of Scio that a lot of our users find super useful was this BigQuery integration enabled again by macro. So BigQuery uses this JSON kind of format for representing data, but JSON handling in Java or Scala is dynamic, it's stringly typed, so it's quite error prone. And the last thing you want to see is your data processing job running for hours at the end, like now pointer exception or fail to cast integer because of these, error prone type errors. So instead, we created macros that takes a user, query, SQL query string input, and then we produce this, in this case, class user, a data type for the class user instead of the user manually typing one. And then you automatically get like autocomplete and type safety from the Scala macro generated types. And the same thing the other way around, the user can provide a type in case of score, and it will automatically provide code, generate code to convert it to JSON and then save to BigQuery. And one of the first job we migrated was, I think, several thousand lines of Scalding in a single job for Discover Weekly, and then we migrated to Scio with the help of BigQuery. And BigQuery being a very optimized execution engine can do like the not so interesting slicing and dicing of data, like just picking the right columns and then filtering the right rows, getting that into Scala, and then we can do the more complex algorithm like machine learning on top of this data. So it's a nice combination of the two. And then some other extra features that we added on top. Some of them are very common in the Scala land. For example, just interactive repo allows users to prototype things quickly. Dataflow can generate this diagram, the directed cyclic graph, and then by annotating the transforms with the source code file name and the line number, we can easily visualize the graph in the web UI. And this helps us as infrastructure engineers. A lot of time when we troubleshoot someone's job stuck, don't even have to look at the source code, just skim through the graph, and you can quickly identify jobs or transforms that's like stuck or spending too much time, or if the data is skewed, like the example here of flat map. Compile time, code derivation, which we'll talk about a bit later. Again, it's enabled by the Scala's powerful macro system that allows us to generate these boilerplate like serialization code in a safe and predictable way. Other things that we do a lot for handling like a huge amount of data, for example, various forms of join, speed things up, of reduce I/O, for example, hash, skew, the sparse join, they handle like different type of skewness or different shapes and size of data, that goes through a join. We try to speed up or reduce the overhead. And then, of course, connectors to a lot of other ecosystem that we use heavily, TensorFlow, Protobuf, Elasticsearch Parquet, and so on and so forth, many more. So years, last 5 years, a lot of libraries ecosystem on top of Scio for not just data processing, but like the add-ons to data processing. For example, BigDiffy is a library for doing difference diff on two data sets on a pairwise field level. So the idea is taking two data sets that's keyed on the same string key, and then we can take, compute pairs of data from records from both left and right hand side. Then we can drill down to the field level, like individual field of integers, strings, or vectors, and then compute the delta being a numerical value. And then with that, over the entire data set of millions of records, we can compute statistics, like what's the minimum, maximum, mean, and standard deviation of the delta. And also can handle like other unique edge cases like non-deterministic fields, if it's a set or list or fields that need to be ignored. So how is this useful in our case? It's pretty interesting. It gives us like a lot of stats. For example, globally, the two data sets, how many records are same, different, how many keys are missing on one or on the other side, and then for each key, what are these breakdown of these differences, and then of course down to the field level, how much is each field different in the two data sets. And this helps us for one in migrating data pipelines. We migrated a lot of Python pipelines with not so much testing and how to, legacy pipeline that's been around forever and how to maintain. We migrated to Scio, and how do you tell if it's processing data correctly? We run the two pipelines side by side and then diff the result. So you see how much the computation differs, and that help us to check the correctness of pipelines. And of course, it's useful in ML. So if you have some drift in some metrics you're computing over time, it's easy to just do the diff and then tell, certain fields differs by, I don't know, 0.5% over, daily or weekly partitions. So these are some of the more typical use cases for diffing big data sets. Feature is another library that we built, again, for machine learning. So, I mean, for those of you who have done machine learning, like one of the most tedious part is just feature engineering, right? Like, clean up data, doing normalization on numerical fields, or like converting categorical fields to one-hot or n-hot encoders. And normally, if you try to do that by hand, you have to write a lot of either SQL statements or transformation that's error prone, and then it might not be as efficient, because if you try to do it one column at a time. And the feature in this case try to solve that problem by offering like a Scala DSL. So you describe what I want to do for each column and then what transform I want to apply. One of these pre-built transformers, encoders, quantizers and binarizers, things like that. You apply them with parameters and it compiles that into a single reduced map data flow job that really just uses one shell for the costly part and then pre-processes your data for all the columns that you want to transform. And this one runs on top of Scio, obviously, and then it supports other runners backends as well. And we can run it both in batch mode offline on huge volumes of data, or you can load the same transformations into a backend service to transform like real-time data. So for example, we often do like batch offline processing, train the model, and then load the same graph into a backend service to provide like real-time predictions. So this is like a high-level overview of how the API looks like. We have some record type account with 3 numerical fields, age, income, balance, and then the last one is the categorical field profession. So we can apply like 4 different transformers to each one of them, and then just a DSL without any like map reduce flat map, like actual transforming code, and this just compiles to a spec that can be applied to, in this case, extracting from a collection of accounts, or in the case of a backend service real-time, it can be extracting from a single account record, and then we get all the numerical features, like in this case, machine learning or what have you. So yeah, some of the examples of libraries that we built, and these are being added almost daily within Spotify. So as of today, I think we have more than 450 engineers, data engineers, using Scio almost on a daily basis, writing pipelines. And we have 4,000, I believe, unique production jobs running every day. So that's a lot. And we use all sorts of storage available to us, and of course, running it in both batch and streaming mode. So yeah, with so many pipelines, so many people working on data problems, it's a challenge to keep everything consistent. So within Spotify, we have our internal ecosystem to manage like these 1,000+ pipeline repositories. We have like internal mono repo that keeps all the libraries dependencies in sync and provide like utilities for the typical, common operation people need to do day-to-day, like encryption, decryption of data, monitoring of data like lateness or correctness. People use counters or metrics a lot to, to verify the data processing is correct. Of course, data quality tools like statistics, profiling, the things that I mentioned, and then of course capacity planning, like the auto scaling, the type of VMs or memory and disk that we need to use for the data processing jobs need to coordinate it within the company. And then we abstract all of these things away into SBT plugins within Spotify. So everybody depends on this common plugin for these common pre-configured settings and tasks, and instead of like copy pasting the same build file over and over again. And there's another open source tool, Scala Studio, that's been like hugely helpful for like keeping everything consistent. So like everybody depends on the same plugin, and then the Scala Studio takes care of automatically bumping all the repositories to keep on the latest version, and then just all the bugs, fixes, and improvements that automatically gets merged. So some deep dive into the more nitty-gritty details of data processing. One of the often like neglected part is actually one of the more expensive part of data processing is actually serializing data. So by taking your in-memory Java objects or records and serializing into bytes. So it happens every time you do anything that requires shuffle, like a group by key or joins or combines that needs to take these records, serialize them into bytes, right, written to disk files, shipped over the network, and then backwards back into records. So this is often the most time-consuming part of a data processing job. And in the Apache Beams SDKs, every P collection, which represents like abstract data type, requires this business logic, the coder, which handles the encoding and decoding the data, just basically taking your value, write it to output stream or read it from output stream, input stream. And before Scio 0.7, actually in many other Java JVM-based data processing framework as well, like Spark, Scalding, Storm, they all use this library called Cryo, and there's a Scala extension for it called Chill from Twitter. So this library is reflection based, so it needs to do a lot of reflection on the Java type objects, and then also serialize the class name into the byte stream. So it adds quite a bit of overhead. Sometimes tens or 20 bytes per record just for a few integers possibly. So overhead from both the inefficiency of reflection and of course the extra bytes overhead for the space. And also because it's done in compile time, we can leverage a lot of the more strict correctness checks that's available to us in Dataflow. For example, one common mistake is using a floating point, like a float or double type is a join key. It's the encoding of it is actually non-deterministic, so it could potentially lead to error. And also another common case like hash map versus a tree map. So whether the encoding of elements are sorted or not, the ordering of elements can affect our correctness, right, in a join. So these elements may or may not compare equally based on the underlying implementation. Same thing with equals, a common or well-known Java problem, like arrays don't have consistent equals. So to compare them, you have to actually compare every single. If you have nested arrays, you have to like recurse into it. So none of these can be done actually using a reflection-based encoder because it doesn't know the type ahead of time, so it can't implement these behavior correctly. And then we fix all of these in Scio 07 with a type-safe coder, which is generated in compile time using this library called Magnolia, which again is a library for like simplifying macro-based type class derivation in Scala. So basically it allows us to traverse through the AST of this data type, like what are the name of the fields and what are their types, and then can traverse them recursively, and then allows us to inject custom logic. So all we need to do, we know how to implement correctly the encoders of all the well-known types, primitives, integers, strings, or the popular Java and Scala collections, hash maps, lists, and whatnot. And we use Magnolia to compose that so we can encode things correctly for like complex data types, like Java Bean or like POJOs, or in Scala's case, case classes. So and allows us to implement all of these correctness behavior, checking encoding deterministic, or consistent with equals allows us to implement these correctly. And then in the case where the macro derivation fails, we still fall back to cryo, which just use the brute force reflection-based technique to serialize the Java object. And the migration is actually fairly straightforward. So if you look at the type signature in the Scio 06, we had this type class tag for every type that's going through our pipeline or collection. So that's a Scala runtime reflection class tag that tells us what the class is, but it doesn't really offer much. Like we can't really inspect the content of the class. Where in the 0.7 case, we have this coder, which implicitly uses the Scala macro to inspect our data type and then compile time generate coders safely and then more predictably. And another nice thing to mention is actually by doing this, we achieved probably 30% speed up across most typical pipelines just because of the more deterministic encoding, decoding, and also reducing the size overhead and the reflection overhead from serialization. Another feature that we introduced recently is this idea called thought merge bucket join. It's an idea from actually the relational database world. So big data is different, right? Like in relational database files, data, rows and columns are stored in a proprietary format that has indexes and primary keys. Whereas in most cases in big data, it's just like a giant blob of gigabytes of file with like just row oriented with no structure whatsoever. So it's the only way to process files is by brute forcing every single byte in a file, which can be inefficient in some cases. So this SMB join borrows the idea from a relational database. So the idea is that if we have a data set that has a key that's commonly used, for example, user name or user ID, and if we bucket data by that key, so each bucket has only a predictable subset of keys, and then we sort all these keys before writing them into file. And the operation of join can be simplified into just finding the matching buckets and then merge sort all the records from these buckets. So it allows us to reduce the amount of shuffle, which is, again, really the most costly operation in big data processing by reducing that and then translating it into a merge sort. So this is like a very simplistic view of how bucketing works. We have this left-hand side original data with lots of keys. We do a hash code on the ID and then bucket them into 3 buckets. And then within each bucket, you can see that the keys are sorted lexicographically, or in this case, the integer. So they're just numerically sorted. This is on the producer side when we write data in this particular format. And on the consumer side, when we need to perform a join on 2 data sets, left and right hand side. And if we know ahead of time that they are both keyed on the same ID and then stored in the same format with 3 buckets, and the join becomes much simpler. We just take one on both sides, perform a merge sort of all the records. So there's no shuffle, there's no n-square shuffle, as we can see, between the left and right hand side, which is significantly reduces the overhead in our processing jobs. So again, the idea is we shuffle once on the consumer side and then join everywhere downstream and benefit from the reduced cost. And it's really helpful in the Spotify case. Like, for example, the most consumed data set, like the one that tracks every time a user plays a music track or podcast, it's hundreds of terabytes. And by just doing that, it's consumed by, I will say, majority of the Spotify data processing jobs, and by storing it in a CMB format keyed on the user, it significantly reduces the downstream processing cost. And it's available in Scio since 0.8. And a nice bonus from sorting all the records by key is that the similar fields are actually more closely collocated, and that offers like a better compression. The algorithm can work better by just finding the similarity in consecutive bytes and then compress them. And there's a little bit of planning required, so we have to coordinate across data producers and consumers to figure out like which core data sets to migrate, and of course what key we want to use. And the semantics matters, whether it's like a hex string or it's a base 64 encoding. We have to agree upon a convention for all data sets to use the same encoding and semantics, and the number of buckets, obviously. But it's a work in progress, and we've already seen some really promising data improvements in our processing jobs. And another deep dive into a more like a product-facing feature called Wrapped. It was actually just released a few weeks ago. So every year at the end of the year, we do this campaign that basically just a recap of everyone's year on Spotify, what tracks you listen to the most, which track new artists you discover, so on and so forth. We do that every year, but it's a really expensive and big job because it's to take into consideration like whole year's worth of data. So 2008, that was maybe one of the early iteration. It was brute forcing, like computing a year's worth of user track play history in a single data flow job, which resulted in the largest data flow shuffle, if I remember, was more than 100 terabytes in a single job. So in data flow history. And 2019 was even more challenging because it was the end of the decade. So instead of processing a year's worth of data, we actually tried to process 10 years worth of data. A little higher level summary for the last 9 years, and then more granular for 2019. And we leveraged some of them optimizations, like using Bigtable as an intermediate storage. Bigtable has some nice properties that we leverage, like the row keys are lexicographically sorted, so we can do like efficient range scans to mimic some of the shuffle behavior. And then we do yearly computation independently, and then in the end aggregate into the entire campaign data. And 2020, that's the one that we just released a couple years ago, was actually using SMB in production. So we have some really promising numbers, and hopefully we'll publish in a blog post later, and so still stay tuned. So this is just a recap of the structure of 2019 Wrapped. So for every year from 2010 to 2018, we compute like higher level stats, like everyone's top artists and tracks. And of course, 2019, the most recent year, we do like a bit more, all these more granular genres and podcast seasonality analysis, and then finally merging all of them in a large job to a final storage, in this case, Bigtable. So everybody gets some roles in the Bigtable, just the aggregated stats from this Wrap pipeline. So two blog posts that you can check out about how Spotify ran largest data flow job, and also the more detailed analysis of the 2019 Wrapped. And the final one, the next step. So we talked about a lot of performance optimizations, things that we work. And we're working on a lot of other approximate algorithms. We recently improved the performance of long filters and hyperlog log. And then support for other runners. We're already able to run Scio on Flink. I know there are users running it on Spark. There's usually some challenges involved, like different ways of deploying pipelines, packaging, some other nitty-gritty details that we're investigating, and more streaming features to support complex streaming pipelines, like stateful do functions, how to keep track of states and coordinate using jobs, refreshing side inputs, things like that. Like a lot of the long running streaming pipeline needs to be able to refresh metadata from elsewhere, external storage, or a static file. And then the last thing that we are working on with EPFL, the Scala Center, is a migration to Scala 3, just figuring out the challenges, like a lot of the macro that we're using and type class derivation, how would they work in the Scala 3 ecosystem. So think that's the end of my talk. So maybe we can save time for questions and discussions.
Yep. Thank you. It was a nice introduction to Scio.
Thanks.
I have a couple of questions on the topic. I don't see any questions so far in the chat, but I noticed that you mentioned like different versions through the presentation, like Scio 0.6, 0.7, and I looked over the GitHub, and it's like you prepared in 0.10 or something.
Yeah.
What would you say your personal pre-requirements for it to be like released of version 1, so to say? Because you showed on one of the slides that there was a Twitter post from something like 3 years ago, and I assume that it's already quite a big and mature technology. So yes,
it is pretty mature. Yeah, I think it's more of a choice or preference. Like, some people use the more strict semantic versioning. So 1.0 means it's going to be a stable API, and I think the Scala ecosystem maybe they tend to work a bit differently than Java. Like Java, the mentality is all about like keeping backwards compatibility, right? Like the legacy code needs to run pretty well. I think Scala ecosystem, we try to like the idea is to move fast, right? So keeping it below 1.0 means that we can choose to break APIs when necessary. In some cases, yeah, users might not like it, but the Scala ecosystem has also a lot of other tooling, like the Scala fix, like the automated, migration or code fix tooling that can just migrate things quickly and easily instead of like some manual work, and that allows us to fix things like instead of leaving a lot of legacy code. So even in Spotify today, I think Scio at this point 0.10 is fairly stable, that we try to avoid breaking changes when possible. But when we have to, for the sake of say consistency or like critical bug fixes, it's nice to not worry about the baggage and move fast. And I hope the users can understand. Within Spotify, we have tooling to automate that. But like external users, we communicate and make sure that they understand this is for the better good. I'm not sure about 1.0 yet. I don't know if it will happen anytime soon. Like maybe when we're confident enough. But like again, I think it's just a psychological
yeah.
rather than like really technically how mature it is. Like we know it's running in production for dozens of companies. Lots of people using it.
Yeah, I was also curious about the external users. Is it? Do you have any figures like how many people use it outside of Spotify?
So there's a powered by page. Right now, there are like maybe dozens of companies that publicly acknowledge using it, and I know there are many more. They probably prefer to not discuss that for whatever reasons. But yeah, I think there are a lot of companies, and there are companies processing possibly even more data than Spotify using Scio. So it's very, very good to hear, actually.
Nice. Okay. Do you some questions on the data, if you can share that? So Spotify is obviously an international company, and you operate in multiple countries across multiple continents and so on. Is it that number of like you pointed somewhere that 4,000 data jobs or something? So when you create a new job, typically it's the same code base that runs across every country, or do you group countries like per continent, or like how that is decided usually?
That is a very good question, actually. For the most part, we try to have the same job that runs on all markets. But for some markets, especially the new markets we're entering, with culturally quite different. Like for example, like different languages or different, like for example, I think for a long time we were primarily in Western Europe and the US, where most people's concept of pop music or favorite music is fairly consistent. But I think that last couple of years we entered like India with hundreds of languages and like very unique culture of consuming music. Like I think the one thing being discussed was Bollywood music, and not even Bollywood, but like movies in different languages. How do we compute that correctly and handle them? And then I guess in the case of Russia, I think when we entered Asia, like Hong Kong, Taiwan, the Chinese-speaking regions, like the script is different. For example, like the language processing, like algorithm needs to be tuned to cater for or handle like the encoding of these languages, and then the machine learning algorithm as well. So in those cases, yeah, I think we have special pipelines just to handle that.
Cool.
And I think the other one was Latin America, again, like because they, the taste, music taste is different. There are unique local genres that we have to cater for.
Okay, so it's more like really you have thousands of jobs and you try to make them as uniform as possible, and just calculate for the different countries. Cool. Yeah. I forgot my question. Yes. All right. Just out of curiosity, how long it takes to just build such tool, so to say? So, like, what's the size of a team? Yeah.
The framework. It's actually pretty amazing. And I think that's a manifest of like the power of Scala as a language. I think the first working prototype I built in like a week. It was very concise. And again, like the idea is pretty established. Like Scala is a very, like the pattern of building Scala on top of Java, right? Just like by providing a nice, concise, idiomatic API that's well proven. Like Scalding did that. Spark has similar idea. Flink also similar. So that's fairly straightforward. The team itself is I think right now 5 engineers. But I mean, over the last 4 or 5 years, it's a lot of work to optimize, like to iron out the edge cases to make it work for like thousands of pipelines in a scalable, performance, and type safe way. So yeah, the first prototype was easy, but it's always the last stretch, the mile that takes a huge amount of work. And then as I said, there's always constantly room for optimization to make it, adding more features. It's happening constantly all the time.
Yeah. You also mentioned that you work with EPFL on that, with the guys who actually develop Scala. Can you share any like experience of working with these academic people and from your point of view?
It's still early stage, but I think they have a lot more insights into how the compiler actually or these advanced features. Also, that would be helpful. But also having like industry, products to work on, so we provide like bug fixes, or reports. For example, I remember we were like the first out of the major like Scala pipelines. We were probably the first to move to Scala 2.12 and also 2.13. And every time we start with like the earlier, it's like 2.12.0, 2.1. We discover bugs with like compiler. We have to report it or make bug fixes. And interesting one to mention, like majority of these pipelines use the Twitter stack, like Chill for serialization I mentioned already in the talk, and then they also use like a closure cleaner, which does like funky bytecode manipulation to make sure your Java compiled, bytecoded serializables that can be shipped to different workers. And we actually did bug fixes in Chill to do that for every time there's a new Scala version. We move pretty fast. We try to stay on top of, and then we work closely with the Scala team. That just they're very responsive, like fixing these bugs and talk to us.
What would you say? Like back to question on the 1 week prototype. It's very impressive that you can build such a framework in such a short amount of time. But what's your like main pain point that made you like, okay, I'll stop everything and build this framework and then go on? What was the driving factor?
I think at the time it was more like I think the idea of running on Google Cloud, like cloud natively, was really appealing, right? Like we want to run on Dataflow because it reduces all the operational overhead. And the native API is Java, which is just not the easiest to work with. It's very simple. The idea behind the framework, the Java SDK, is very simple, but It just Java tend to have this very, very boilerplate. Like you have to write a lot of code to do simple things. And a lack of certain features like implicits and type classes make it hard to abstract complex ideas away and have very simple DSL. So that's really the main motivation. And at the time, I think Scalding was great. It runs really well on Hadoop, but we want to move away from Hadoop. So that's another motivation. And this again, this I think the other I think often neglected part was Beam itself offers a new way of doing data. It's not just batch on files anymore. Like you can do batch and streaming, and then you can interrupt with any of the storages, like databases or file systems or like streaming, PubSub, Elasticsearch, any of these. So it's basically like a hub of all these data processing components that we use.
Cool. And in terms of the journey, so you said it was like on-premise first with that nice Hadoop cluster next to Fuse table. Then you went to the cloud, and then you came back to on-premise, and now you have like your own cloud, basically.
Yeah.
Yeah.
So yeah, the first one I don't think it lasted very long because it's tiny. As you can see. So moving to Amazon was because at the time they were probably the only option for like running large Hadoop jobs.
Mm-hmm.
There's a fair amount of overhead. Like EMI. I think we back in the day we spin up new clusters for every job, and that's a fair amount of overhead. Just like waiting for the VMs to spin up and down, and the VMs were not at the time. Again, I was almost 10 years ago. Was not as powerful as like bare metal servers. I remember the Hadoop nodes that we have was like lots of RAM, lots of CPUs, and lots of disk. Like everything's fairly optimized. So that's when we moved to on-prem because that's for both cost and scalability reasons. Moving to the cloud was just more like the trend. Everyone's going through that phase. I think a lot of companies are going through that. Like it's very hard to maintain your own data center, like not just managing the hardware and also deploying your own cluster, have operational teams. So it's I think it's a natural evolution in big data processing.
Would you say, like, just I know that it's hard to predict, but you would say that right now on-premise is like fully satisfy the needs of a company, and you will probably never move back to the cloud, or
Not really, because I think the cloud running on the cloud enables more rapid prototype or experimentation. Like on-prem, I think the biggest hurdle, at least for me as a developer at the time, like you have to order machines. For example, you want to try a new technology, we can do it on the production cluster. I mean, some companies have multiple clusters. For example, one dedicated for prototyping or experimentation. So it depends on your setup. In our case, if you have to order machines and then have hardware engineers set it up, that's time consuming. Where on the cloud, a lot of the vendors have integration with other platforms. Like if you want to try, say, a different way of processing data, like you want to try Snowflake or some other vendor that also runs on the cloud, you can do it quickly. Just open up some API and access, and you can try that.
yeah. So right now you work only with Google solution, but like, is there any way or any other like providers for such functionality that can be used with Scio? Like, is it just the API, or did you consider any others?
Yeah, it's definitely possible. I mean, I know people who run Scio on Flink, for example, on other cloud. Like we run on Google on Dataflow because it's a natural choice. Like because Beam was majority like maintained by the Google Dataflow team, so it works really well on Google Cloud. And also running on Google Cloud means there's no operations. But I think if you there's a Beam like compatibility chart with different runners, I think Flink is the closest with the Dataflow model, like the both unified batch and streaming model. So it's like feature parity wise, it's the most mature, and there are a lot of people doing that, like running Beam or Scio on Flink and on other clouds.
Okay. Would you say that say that I have for example, a Hadoop cluster that is a local cluster, and I have a rather empty Kubernetes cluster available. Would you say that Scio is so good that it would worth to switch to using that and just move all your infrastructure to Kubernetes just to be able to use this type of thing? Or like, what would be the criteria to do such a move?
I think it depends on the use case and what your main goal is. I think the main attraction of Scio or Beam is that it's portable, so you can write it once in case you want to say move from Dataflow to Flink or back the other way around. It's possible, right? Because it abstracts away the execution framework, so that's nice to have. And also you can just instantly leverage all the I/O components like the connectors with Kafka or Elasticsearch or any whichever one you want that's available out there. You can use it right away. Of course, abstraction comes with a cost. Like it can only abstract the most common denominator, right? So there are optimization that you can do, based on the framework that you're you're executing on, like Spark is in-memory caching or like the RDD's in-memory caching and also iterative. You can have access to the underlying like storage, the in-memory partition, things like that. These are abstracted away from the Beam model, so you lose access to some of these optimization. But then your pipeline is more portable, so it's a matter of choice. I know there are companies with like maybe one or two pipelines that power majority of their business. They probably want to optimize more out of that one pipeline to have a more performance or does the job better. And there are companies with, in our case, thousands of pipelines. So having them in a portable, like concise way, easy to write, nice abstraction, that's attractive. So it depends.
Yeah, okay. I guess that's a general answer to such questions. That really depends. But speaking of other thing you mentioned, Spotify is in Python world is very known for Luigi, and what I heard that it's not really well developed nowadays, and even at Spotify, people stopped using it and just transitioned it to Airflow. Would you say that's actually true, or like, can you confirm or deny that?
We still use Luigi, but mainly for the orchestration part of it, mainly for legacy. So Luigi, like as I mentioned earlier, so Luigi has two functionalities. One is writing MapReduce jobs in Python, but those are for those who have tried to write MapReduce streaming, Hadoop streaming in these languages. It's pretty low level. You have to like process individual tuples right in and out, and it's error prone because it's Python. So like the habit or like the majority of the Python community tend to write it in this like rapid prototyping way, but without proper like enough test or type safety to guarantee the confidence in the performance and in the correctness of the pipeline. So that we moved away. But Luigi is still like primarily used for like orchestration. We tried some teams tried Airflow, but because majority of the infrastructure, like all these other challenges I mentioned, like lineage, metadata management, orchestration, they are all tied to Luigi. We're still using Luigi for that, but development is not as active because there's just not a scheduling framework. The scheduling framework it checks if your dependency is available. You add hooks to it to trigger like downstream jobs and then report like success, failures, or things like that. These already there and these have been there forever.
Yeah. Okay. So what would you say like the main feature of Scio that you expect to be released that is in the nearest future? What are you actually working on at the moment?
I think the Scala 3 thing is something we want to work on. I mean, it will probably take a long time just because the ecosystem, you have all the dependencies and some challenges that we see. We want to add or improve the streaming support as well. Like some of them are like conceptually, like it should work on paper, but it needs nice abstraction. So if you look at the Beam abstraction, the data model, it's quite complex. It supports a lot of things, but for average, like for user who don't really care enough about the academic side of this, streaming system design, we want to jump down quickly, right? So having Scala or DSL, say this is a well-known pattern how to do these things. Like the things I mentioned, managing states or managing the reflection side input. Our job as a library designer is to make sure it's easy to do the right thing, and then the error-prone part of it is hidden away, that or like something that we take care of. So it's exploring these domains, like finding what are the common things everyone wants to do, and then we want to make sure they can easily and quickly do it, and also in the correct way.
Okay, I see. I actually don't have any questions, I would say. So
You can add me.
maybe,
Chat.
yes.
Hello. We have a couple of minutes, so I want to ask you this. So Scio is an open source project, right, with Apache license, Apache 2.0. So do you have users of this project outside of Spotify, and do you have any process of communicating with external contributors and with the community?
Oh yeah, we do. So as I mentioned earlier, there's a powered by page. So we encourage users to just submit a PR, add their names to it, and there are dozens of companies there. And there are a couple more that I talked with at conferences, that are not on there, but we know there are other companies using it. In terms of communication, we have publicly a mailing list that you can join, and then a Slack channel also. We hand out and people ask questions. Of course, all the other like standard open source channel like GitHub issues, Stack Overflow, these all exist, so we communicate them. And yeah, since this like working from home situation, we try to do we ran like a virtual hangout meetup once, and then try to hopefully we'll do more like in the future. And then people showed up and then they tell us how to use it, how they use it, and then what they like or dislike, and it's great to hear those things. Hopefully we can do more of that.
What are the top problems that contributors outside the Spotify trying to solve in Scio? Like I see just 3 pull requests, public pull requests, like adding memcached.io, adding sparkly.io, etc. Could you say something about this?
Yeah, so these are the ones that's open. We try to close PRs as soon as possible. And usually it's other different types of storage. Like most recently was one on Parquet, because some other company uses it more often than us. So it depends. The core functionality has actually been pretty stable so far. Like we haven't, done any major bug fixes in the core library part, but it's usually the peripheral. Because if you look at it, it's like 18 some modules like just interact with other storage systems or different types of processing systems. So usually in those areas.
Okay. We have just 1 minute left, so I suggest you to switch to discussion zone, right?
Okay.
For viewers, you have a button to switch to Zoom. So goodbye and see you later in the discussion zone.
Yeah.